In this question, you can see that there is a hollow tube of length L, and this tube is having an inner radius of R1 and outer radius of R2. This tube has a thermal conductivity K, and its ends are maintained at the temperature of T2 and T1, and in such a way such that the complete outer end, which is the outer curved surface of this tube, is maintained at temperature T2, and the inner curved surface is maintained at temperature T1, and T2 is greater than T1, and heat is flowing from outside to inside because obviously T2 is greater than T1. So we have to find out the rate at which heat is flowing from outside of the conductor to inside. Now, first of all, let us see that this conductor has a variable. If heat is flowing like that, so the length of the conductor would be this one. Total length would be R2 minus R1, because length is always measured in the direction of heat flow. Now we will face a problem that the area of this cylinder would be variable, because let us suppose that there is a cylinder of radius x. So the curved surface area of this cylinder of radius x will be 2 pi xl. And as we will move from outer part of the cylinder to the inner part, the radius is variable, and therefore the curved surface area is variable. So therefore the cross section area through which heat is transferring from outside to inside is variable, and therefore we need to do the integration. So for integration, let us suppose that there is a thin cylinder of thickness dx and radius x. So the area of cross section of this thin cylinder will be 2 pi x into L, because the length of this thin cylinder would be equal to this L. And we can say that its width is dx, therefore its radius dr will be equal to dx upon k into a, which is 2 pi xl. You can imagine that if heat is flowing through this thin cylinder like that, then its length in which we are using in resistance, that R is equal to L by Ka. So L is that length through which heat is flowing. So heat is flowing from this part in this direction, therefore this length is dx, and the area is 2 pi xl, and K is the thermal conductivity. So the total resistance R will be equal to 1 upon 2 pi k L ln x, and the limit of this would be from R1 to R2. You can integrate in either direction, and obviously keeping in mind that resistance cannot be negative. So R will be equal to 1 upon 2 pi k L ln R2 by R1. So this is the resistance of this cylinder, and therefore the heat current flowing from outer part of the cylinder to the inner part will be delta T upon R, and therefore I will be equal to delta T is T2 minus T1 upon R is ln R2 by R1 divided by 2 pi KL. This is the current which is flowing from the outer part of the cylinder to the inner part. Now we move on the next question. In this question, you can see that there is a steel rod of K, which is 42 joule per meter per second per degree Celsius, and this has a length of 1 meter. This one end of this rod is kept in ice at 0 degrees Celsius, and the other end of this rod is kept in boiling water. The area of cross section of this rod is 0.04 centimeter square, and there is no heat loss to the atmosphere. So we have to find out the rate at which the mass of ice melts. It is also given that the latent heat of fusion for ice is 3.36 into 10 raised to power 5. Now obviously we have to find out the resistance of this rod first of all. So resistance would be L by Ka. So L is 1, K is 42, and the area of this rod will be this is 4 into 10 raised to power minus 6. You can see that this is 0.04, so we can write it as 4 into 10 raised to power minus 2, and we have converted the centimeter square into meter square by multiplying additional term of 10 raised to power minus 4. Now this is the resistance, which is 10 raised to power 6 upon this is 168. Now you can see that the temperature difference delta T between the two ends is 100, and therefore the heat current dQ by dt will be equal to 100 upon R, which is 10 raised to power 6 into 168. So this is 168 into 10 raised to power minus 4. And this Q will be equal to 168. In fact, we can write down dq as dm into L. So dq by dt will be equal to dm by dt into L. So 168 into 10 raised to power minus 4 is equal to dm by dt into 3.36 into 10 raised to power minus, in fact, plus 5. So dm by dt will be equal to 168 divided by 3.36 into 10 raised to power minus 9. So this is in kilogram per second. So if we find out in gram per second, so it would be 168 divided by 3.36 into 10 raised to power minus 6 gram per second. So you can see that this will be 168 upon 3.36. So you can see that it will be 16.8 by 3.36 into 10 raised to power minus 5, and this is equal to 5. So it is 5 into 10 raised to power minus 5. So this ice is melting at a rate of 5 into 10 raised to power minus 5 gram per seconds. Thank you. In this question, it is given that there is a spherical shell whose inner radius is R1 and whose outer radius is R2. The temperature of the inner surface is θ1 and temperature of outer surface is θ2. So we have to find out the radial distance of that point from the center, where the temperature is just halfway between θ1 and θ2. Now what does it means? That let's suppose at a radial distance of small r from the center, the temperature difference is just half. Now it means that the resistance which is inside this radial distance r is, let's suppose, small r1, and the resistance outside that radial distance r is small r2. So it is given that the temperature difference of these two should be equal, because this temperature difference at this point should be just half of this one and this one. So this is θ1 and this is θ2, and this temperature difference should be just half of this difference. So it means that in series combination, this is in series combination, for half temperature difference, we can say that the value of resistance R1 and R2 should be equal, and the resistance of this small section of width dx and radius x will be dr, and dr will be dx upon the surface area, which is 4 pi x square. So the resistance R1 will be integration dx upon 4 pi x square into k. K is the thermal conductivity, and this is k, and the limit of this would be from in fact r1 to r. We are assuming that till this point the radial distance is r. and the R2 resistance will be equal to integration dx upon 4 pi x square k from R to R2. So when we will integrate these two and we will equate, because R1 will be equal to R2, we have already concluded it. Therefore, we can write down that dx upon 4 pi k x square integration from R to R1, or R1 to R. This is R1 to R, and it is equal to dx upon 4 pi k x square. Limit is from R to R2. So cancelling 4 pi k with 4 pi k, the integration of 1 upon x square will be minus 1 upon x, and limit will be from R1 to R, and integration of this would be minus 1 upon x, and limit would be from R to R2. Cancelling this minus with minus, we can say that 1 upon R minus 1 upon R1 is equal to 1 upon R2 minus 1 upon R. So you can say that 2 upon R is equal to 1 upon R1 plus 1 upon R2. And you can say that R is equal to 2R1 R2 upon R1 plus R2. So the correct answer would be option number C. You can see that 2R1 R2 upon R1 plus R2. Now let's move on the next question. In this question, you can see that there is a cubical box in which there is a source of energy. This source of energy is at some temperature, and it is generating a heat of 36 calories per second. Now this covering this walls of this source, cubical source, is insulating, and the heat transfer is being done by these resistance plugs. This is resistance plug. The area of cross section of each of them, each means this one, there are two plugs, this and this. So this complete area of cross section is 12, its length is 8, and its conductivity coefficient is 0.25. Now this end is maintained at a temperature of 100 degrees Celsius, and this end is maintained at a temperature of 4 degrees Celsius. So we have to find out the equilibrium temperature of this source of energy. So let us first of all assume that the resistance of this single plug R is L by Ka, where L is 8, area is 12, and K is 0.5. Now you can see that this resistance is in centimeter, this K is in centimeters, this area is in centimeter, length is in centimeter. So you need not to convert the units, and therefore R will be equal to 16 by 12. So it is 4 by 3. Now this is the resistance of this single plug. There are two resistances. Now we will assume that the temperature of the source is T, and therefore the heat flowing through this plug in this direction, and the heat flowing through this plug in this direction, Q2. The sum of these two heats will be 36, and the Q1 will be equal to T minus 100 upon the resistance R, plus Q2 will be equal to T minus 4 upon resistance R. This is 36. So you can see that 2T minus 104 is equal to 36 into 4 by 3. So 2T minus 104 is equal to 48, and 2T is equal to 152. So T will be equal to 76. So the correct answer will be option number C. Now we move on the next question. In this question, you can see that there are two rods, of one of steel and one of brass. The left hand of this steel rod is maintained at a constant temperature of 100 degrees Celsius, and the right hand of this brass rod is maintained at a temperature of 100 degrees Celsius. Now the junction is also maintained at a temperature of 50 degrees Celsius, which means that heat will be flowing in this direction. This is Q1 and this is Q2. And this combined heat is Q1 plus Q2 is being taken out by some way from this junction. So the combined heat which is taken out from the junction is Q1 plus Q2. Now we have to find out this heat. Now we know that Q1 will be equal to temperature difference across steel, which is 50, upon the resistance of the steel, which is L by Ka. Now L of each rod is given as this, and the value of K is in standard units. So you have to convert the length into meters. So this is 31 into 10 raised to power minus 2. Area is in a centimeter square, so it is 0.2 into 10 raised to power minus 4. And the K of steel is 46. So this is Q1. So Q1 is equal to, this is 50, in fact, this is 10 into 10 raised to power minus 2 into 46 divided by 31. So Q1 will be equal to 46 by 31 into 10 raised to power minus 1. Now the value of Q2 will be equal to, this is temperature difference is 50 and length is 31 into 10 raised to power minus 2. This is 0.2 into 10 raised to power minus 4, and K of brass is 109. So you can see that Q2 will be equal to, this is 10 into 10 raised to power minus 2 into 109 divided by 31. So Q2 will be equal to 109 by 31 into 10 raised to power minus 1. So Q1 plus Q2 is equal to 109 plus 46 divided by 310. So this is equal to 155 divided by 310. So Q1 plus Q2 will be equal to 1 by 2. Now we know that we have calculated Q1, Q2 as heat currents. So we have to find out the total heat. So the total heat which is taken out, Q total, will be equal to total heat current, which is 1 by 2 into time. Time is 10 minutes. So 10 minutes is 600 seconds. 600 seconds. So it would be 3 into 10 raised to power 2. So N will be equal to 3. Now we move on the next question. In this question, you can see that there are 4 identical rods. This is AB, this is AC, this is BD, and this is EF. They are identical. And this is the midpoint of rod AB. So the temperatures of these ends are shown, and there is no heat loss to the surroundings. So we have to find out the temperature of this joint. So let us suppose that the temperature of this joint is T, and the resistance of each of them is equal to R. So the resistance of this one, which is the half length of AB, will be R by 2, and this will be R by 2. So let us draw a circuit, or let us apply the nodal analysis. So let us assume that the temperature of junction E is T. So the heat current flowing through this end will be T minus T2 divided by the total resistance. So the total resistance of this will be R plus R by 2, which is 3R by 2. Okay. Plus the heat current of this end will be T minus T3 divided by R. And the heat current of this end will be T minus T2 divided by 3R by 2. And this will be equal to 0. So you can see that if we find out the LCM, then we can say that equation would be LCM would be 3R, and the equation will be 2T minus 2T2 plus this would be 3T minus 3T3, and this would be plus 2T minus 2T2, and this would be equal to 0. So this is 7T, and this is equal to 2T2 plus 3T3 plus 2T2. Okay, and in fact this is T1. So this is T1. So this would be T1, and hence this is T1. So this 2T2 plus 3T3 plus 2T1 is the total, and we have to find out the temperature of the joint. So T will be equal to 1 by 7 of 2T2 plus 3T3 plus 2T1. So if you compare it with K, then the value of K will be 7. Now we move on to the next question. In this question, you can see that there is a hollow spherical shell of inner radius R1 and outer radius R2. It is placed inside a reservoir of temperature 1000 degrees Celsius, which is maintained constant. Now there is some water inside this shell at 0 degrees Celsius, which is the initial temperature, and it is not maintained constant. And the thermal conductivity of this material of the shell is this. Now we have to find out the time required to raise the temperature of this water from 100 degrees Celsius to time required to raise the temperature of the water to 100 degrees Celsius from 0 is this one. So we have to find out the value of K, and the specific heat is given as this and density is given as this. So let us first of all find out the resistance of this shell. So we know that the area of cross section of this shell is variable, and the heat flow will be like that, and therefore the resistance dr of a small elemental shell will be dx upon 4 pi x square into K. K is the thermal conductivity. So the total resistance R would be 1 upon 4 pi K, and this total resistance will be calculated by integrating. So the limit will be from R1 to R2. R1, R2 are the radius. So R is 1 upon 4 pi K, and the integration of 1 upon x square will be equal to minus 1 upon x. So the integration limit would be interchanged by using that negative sign. So R will be equal to 1 upon 4 pi K, and the limits would be 1 upon 0.25, which is 1 by 4, minus 1 upon 0.5, which is 1 by 2. So R will be equal to 1 upon 2 pi K, where value of K is this one. So 1 upon 2 pi, and this is 10 raised to power 2 by 4 pi. So it is 2 divided by 10 raised to power 2. So R will be equal to 2 into 10 raised to power minus 2. Okay, now we see that the temperature, initial temperature of this water was 0 degrees Celsius. And let's suppose that the mass, in fact, we know that the mass of the water is its density into the volume of inner shell, because it is completely filled inside the inner shell. So the volume of inner shell will be 4 by 3 pi R1 cube. So mass will be equal to, density is 10 raised to power 3, you can see that, and this is 4 by 3 into pi into R1 cube, where R1 is the radius, this one. So this is 1 by 4 whole cube. So this is the mass, which is pi by 3 into 10 raised to power 3 divided by 16. So you can say that m will be equal to pi into 10 raised to power 3 divided by 48. Now we know that the temperature, inner temperature of this water, the temperature of this water inside the shell is variable. So let's suppose at time t, the temperature of the water is T degrees Celsius. So at that time, dq by dt, heat current, will be equal to 1000, outer temperature is 1000 fix, minus T divided by R, where R is the resistance. So R is already calculated, which is 2 into 10 raised to power minus 2. So R is 2 into 10 raised to power minus 2. Okay, so this is the, and dq is ms dt, where dt is the change in temperature. So m, we have already calculated the value of m, which is pi into 10 raised to power 3 by 48, or we can substitute it later. So this is ms dt by dt is equal to 1000 minus t divided by 2 into 10 raised to power minus 2. So dt by 1000 minus t is equal to 1 by ms into 2 into 10 raised to power minus 2 into dt, and integrating both the sides. The limit of temperature would be from 0 degrees Celsius to 100 degrees Celsius, and the time would be from 0 to T0. And we have assumed that T0 is the time in which the temperature of water will reach 100 degrees Celsius. The integration of this side will be ln 1000 minus t, and its limit would be from 0 to 100, and integration and divided by minus 1, and integration at that side will be T0 upon ms into 2 into 10 raised to power minus 2. So when we will substitute the limits here, then let us use this negative sign and let us invert the limits. So if we substitute the value 0 at this at the place of t, so it would be ln 1000, and when we will substitute the value of 100 at the place of t, it would be 900, and here it would be T0 upon ms, where m we have already calculated. It is pi into 10 raised to power 3 by 48. And s is equal to this one, 4.2 into 10 raised to power 3. And this is 2 into 10 raised to power 2 minus 2. So T0 will be this is 24. So T0 will be equal to, this is 10 raised to power minus 4, in fact plus 4, into pi into 4.2 divided by 24 into ln 10 by 9. So we have to find out the value of this 1100K. So if we equate it with 1100k, so you can see that it is given that pi is 22 by 7. So this value is equal to 1100k, and this is pi into 4.2 divided by 24 into 10 raised to power 4. So this is 11k is equal to pi into 4.2 divided by, in fact, we can write it as 420 divided by 24. So the value of k will be equal to pi into 420 divided by 11 into 24, and if we substitute, now we again write down the value of k as pi into 420 divided by 11 into 24, pi into 420 divided by 11 into 24, and if we substitute the value of pi as 22 by 7, so you can see that this is 2, this is 12, and this is 60, and this will be 5. So the value of k will be 5. So the correct answer of this question will be 5. Now we move on the next question.